Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
All right, well, I was going to try some new technology, but as always, these things are kind of fragile and crash easily. So we're back to this one. I'll try it, see if I can get it to work next time. But in the meantime, we've been talking about Bayesian inference. Now, Bayesian inference, as you know, is a more subjective way, but it's a very useful subjective way to come to conclusions on the basis of information. So what I alluded to at the end of last time, we'll sort of we'll go through it with a very quick summary and then continue where I was last time. Very quick summary. I'm going to use F, even though sometimes it'll actually be P. So I'm going to use F for a density, and occasionally it'll be a mass function instead of a density, and I'll just use F so that I'm going to try and minimize notation when I do this. So you've got some prior density on a parameter, and it could be multiple, in which case it would be a joint density. But for the moment, it's just a single parameter, prior density F of theta. And then you have the observation. And then you have a conditional density. So I'm just reusing F for all these different things, and you can see from the parameter. Conditional, usually we used to think of this as an unconditional density, just the density of the observation. But now we're doing Bayesian things, so think of it as conditional density, because theta could take a whole lot of different values with different probabilities. And conditioned on that particular parameter value you choose, so theta is the unknown parameter, then you have an observation x. And this is also called the likelihood. Remember that the likelihood of theta is the conditional density of x given theta, not the conditional probability. So it's quite different. So the posterior distribution is given by the density f of theta given x. Okay? So as before, this is exactly equal to the prior density f of theta times a correction factor to do with what observation you've made, and the correction factor is f of the observation probability, f of x given theta, and then divided by the integral over all possible values, f of I almost don't want to reuse theta. But let me make this theta naught, conditional density of x given theta naught. And then remember what we're doing here. We're doing a joint divided by a marginal. So I should be doing the joint of theta and x. That's this times that is the joint of theta given x. And the denominator should be the marginal of x. To get the marginal of x, you integrate out the unknown, the variable you don't care about. So this is d theta 0. Okay? So that's exactly what the posterior density equals. Okay? Now the first thing to remark, which I did mention last time, it doesn't matter if you dropped a constant, you omitted or dropped a constant in the likelihood of theta. Because if you did, you'd have the same constant in numerator and denominator, so you get the exact correct posterior. But the second remark is, which I won't even write as a remark, but often if we're just trying to recognize a density, and also for some other purposes, we even don't want to get the exact density. It's enough to get proportional. So it's enough to say proportional to f of theta, f of capital X given theta. And that's because, and I'll put in parentheses here, this is for fixed x. Now, of course, we are usually thinking about fixed x. If you want the exact correct formula across all x and theta, you should use that formula. But if you don't care about the exact formula across all theta and x, you just want to let x be fixed and recognize something, this is fine. Because whatever the denominator is, it depends on x, but x is fixed. So whatever, it'll just go into the constant. So that's, in practice, that's the most common way we update our densities. And so let's, that's the first part of inference. That's just the basics. And then that means you think of this as the density of theta after seeing the observation. Okay, so you had a prior density, which was your first idea, and now you've got a better idea of what theta looks like. It'll tend to be narrower in many cases because you'll have more information. So that's how you get it. So let's and recap of the ways of doing point estimates. There are many ways you could do, but just to recap, you could have posterior mode. Mode always means the most frequent result. So in the mass function, it's just the highest mass function. In the density, we say it's the highest density function. So that's the maximize over all different choices of theta, f of theta given x. Okay, you've seen x, so x is a constant, so you just maximize that. And the posterior mean, you can do for not just theta. You can, I mean, it would be pain to have to transform densities to find a density. So mean is more robust. You can do it to any function, and it's nothing other than a conditional expectation, like of f of theta. Actually, I won't use f because f is often a density, so I'll call it t. Some function t. If it doesn't matter what function, so long as you can do this integral, which in the case of a discrete parameter would be a sum, but normally we do integral t of theta, f of theta given x, d theta. Okay, so easy enough to find. So let's do the case where, and those are the point estimates and the interval estimate. It is, of course, L of some function L of the observation less than theta less than u of the observation, such that the probability of that, given x, of course, it all depends on x, should be equal to 1 minus alpha. And that is called the 1 minus alpha Bayesian credible interval. So credible is used instead of confidence because that's kind of a credibility theory is more often associated with this way, although those who've done in STAT6013 will see that there's a lot more to the credibility theory than just this basics of Bayesian inference. But this is called a 1 minus alpha Bayesian credible interval. Easiest, and the only way we'll do it, the easiest way is to set alpha over 2 probability on each tail. Okay, and this is to find the Bayesian credible interval is nothing other than finding the quantiles. Because if this is the density of theta given x, that's some density, you just find the alpha over 2 quantile and the 1 minus alpha over 2 quantile. And this is the Bayesian credible interval. It's just everything in here. And that clearly has 95%, or 1 minus alpha proportion of the posterior probability. So let's continue with an example from last time, which was to do with a particular conjugate prior. Conjugate prior is when there's parameters that just update in an easy to track fashion. So that last time was that if the proportion P had a beta alpha beta distribution, and say that you have some observed K given P has a distribution binomial in P, I'm of course allowed to depend on P, then P given K, we have to, well, we did the calculation last time, I won't repeat it, but except to say, okay, yeah, I will repeat it just in as quick as I can to show you that by using this proportional to method, you can do things very quickly. So the way I do that is I'm going to say density of P is proportional to P to the alpha minus 1, 1 minus P to the beta minus 1. Because all the things at the front didn't depend on P, I can omit them in this form of words. And now I have the density of let's say K given P. Now you'll notice this is all quite sloppy compared to what I was doing earlier. I don't put any subscripts on F, and I also haven't been distinguishing between lowercase and capital K. All of that, if you know what you're doing, you won't make an error, but I'm just not distinguishing between those things. So we know that this is also proportional to P to the power K, which is the observed successes, 1 minus P to the power n minus K observed failures. Now it seems very odd not to put in the front factor here, which after all does depend on K. The front factor is, I might put it in red or another thing, just because it is there, but we can avoid it through the Bayesian calculation. It's n choose K. Now it depends on K, but it doesn't depend on the parameter P, and P is the main game. So, of course, there is this n choose K, but I'm just going to feel free to omit that for the following calculation. That means the density of P given K is proportional to density of P, density of K given P. And I really shouldn't, you see, the other thing that I'm being sloppy about, I'm using F for what is actually a mass function rather than density. But still, it doesn't matter, you get the same. So this stops me having to put P out the front and also as a parameter. So F of P, F of K given P. So, okay, so for those following along, I'll just say this one is actually a mass function, of course. But it's fine to use F for the mass function in this context. In fact, you'll find the other set of notes that's on the website just uses F for mass function universally, which can be confusing. So F there is a mass function. This one is a genuine density. So it's proportional. So that is equal to, even those, by forgetting some constants, I can do P to the alpha minus 1, 1 minus P to the beta minus 1, P to the K, 1 minus P to the n minus K. And you've done so many beta things that you're used to recognizing this as proportional to the actual density of a certain beta, alpha plus K minus 1, 1 minus P to the power beta plus n minus K minus 1. And let me just put in, now all I'm going to do is I'm going to observe those superscripts, and I actually know the constants that go here. Gamma of the sum of those two on the top, alpha plus beta. I had a capital N and a lowercase k, that's not so great. Maybe a lowercase n and a capital K. The k's cancel out, alpha plus beta plus n divided by gamma alpha plus K, gamma beta plus n minus K. Okay, so I just know that constant because I know this is a beta. There's only one constant that works for a beta. So P, to summarize, we would say that this has a distribution beta with parameters. just as before, alpha plus k, beta plus n minus k. So that is the posterior distribution. You can now do your various posterior estimates. So let's do the posterior mode first time. It's kind of easy to believe that, as p increases and 1 minus p also decreases. So there's a certain point at which the decrease takes over from the increase, and that's the maximum. So to find that, we're not going to go through all the details other than just to say that we set partial derivative with respect to p of posterior density k equals 0. Okay, and that partial derivative with respect to p is equal to, I'm just going to leave the density there. It's often easier to write densities in a multiplicative form because the product rule will say, when I differentiate, you can actually do that in a formal way by talking about log f, but log likelihood. It's although it's not log likelihood, it's log of posterior probability. Because when we did maximum likelihood, the natural thing to do was to differentiate log likelihood. When we do maximum posterior density, which is the posterior mode, it's natural to differentiate log of posterior density. But here I won't do the log, I'll just put that constant out the front, and then you see what's left over is this alpha plus k minus 1 divided by p. You see, if I differentiate this factor, I get alpha plus k minus 1 times p to the power 1 below. So that's taken care of by that. And then minus beta plus n minus k minus 1 divided by 1 minus p. So this is just the general calculation for finding the mode of a beta distribution with these particular parameters. So if that equals 0, you can check the calculation yourself if you like, product rule. The mode of these is obtained when the ratio of, basically that's going to be equal to that when the ratio of p to 1 minus p is equal to the ratio of this to that. So clearly that means p has to be equal to alpha plus k minus 1 divided by the total. So it's going to be, p is going to be that divided by that plus that. Alpha plus beta plus n, the k's cancel, and there's a minus 2. So that is the posterior mode. Okay, I'll call this p hat 1 because there'll be another method which gives you a different answer. Posterior mean, okay, would be p hat 2, which is expected value of p given k, which of course is integral of p posterior density. So without going through all the rigmarole, we're very used to what happens when you do this for a beta. You get a p in there and then it's 1 power more. So the actual cancellation on the, you'll get gamma alpha plus k plus 1 on the numerator. That cancels with this with a factor of alpha plus k. And on the denominator, you have alpha plus beta plus n. So it's kind of interesting that they're very similar formulas, p hat 1 and p hat 2, but, the numerator and denominator are just off by a little bit. In the limit as k and n tend to infinity, there's no difference because it's, k and n are going to be very large and it's just minus 1 and minus 2, small difference. But for the lower cases, it can make a difference. So there are ways of evaluating those two methods, but we're just going to say those are two ways you can do it. Of course, sometimes you can't do the integral. So if you can't do the integral, then it might be easier to find the maximum. Or if you can't find the maximum, so sometimes there's practical reasons. We can also do posterior mean of a function. So let's do a particular function you might want to do. What is the posterior mean of the variance of k given p? This seems like a strange thing to do. But you might think, I've got a k with an unknown distribution, and I want to estimate its variance. Well, its variance depends on the distribution. So one way to estimate its variance is to take the conditional expectation of its variance conditioned on the parameter that you saw. So just to simplify this, I'm going to say k given p. You look straight up at the start and you say this was our observation. It is a binomial, and I know the variance of a binomial. It's np 1 minus p. Right? That's just what it is. So your posterior mean is going to be, now this will look very strange. Variance of k given p given p. sorry, not given P. The posterior mean is given the observation. So first of all, I have K given P its variance, and then now given the observation. So don't get confused by this. It's two different steps. First of all, you find the posterior. First of all, you find what is the variance at a particular P-value, and then what is the posterior mean of that. If you interpret it the other way, you might think, oh, K is constant in here, so variance is variance of a constant, which is 0. But that is not what is meant. It's the other way around. So to be super clear, I just substitute in what this means. Expected value NP 1 minus P given K. Okay, so I just integrate NP 1 minus P, posterior density F of P given K dP. Okay. I guess I didn't put in the limits of integration, but for parameters that can go from 0 to 1, proportions and betas, they're always going from 0 to 1. So NP 1 minus P, F of P given K dP. We look back at what this is equal to, it's going to be, well, there's certainly a factor of n. The P bumps up the power of this guy by 1, and the 1 minus P bumps up the power of that guy by 1. So what you're actually going to get used to, you can do you've probably done this beta exercise before. You'll get alpha plus K, you'll get beta plus n minus K. And then on the denominator, you'll actually have alpha plus beta plus n plus 2. And you have to compare that to alpha plus beta plus n. So you get alpha plus beta plus n plus 1. Alpha plus beta plus n. So check your unrolling of, remember, all you're ever using there is gamma of a plus 1 equals a gamma of a. We've used this about a million times. So that's quite a complicated formula. But what it takes into account is it takes into account the prior and the observation. That's why it's a more complicated formula than frequentist formulas. So let's, okay, and let's not do a Bayesian credible interval. I'll just say hard here, because we don't have the, we don't have the quantiles to get a of the beta distribution, okay? But it is, the Bayesian credible interval, the 1 minus alpha BCI for P is, let me just call it, okay, U alpha over 2, comma, U 1 minus alpha over 2, which is, these are just the relevant quantiles of the posterior distribution. And remember the posterior distribution, P given the observation K is beta alpha plus K, beta plus n minus K. Now, because we don't have tables of that, so I'm just going to leave it at that. For other, if the posterior distribution happened to be a normal or a chi-squared or an F, we could do it from our tables. Okay, that's that will get narrower. That Bayesian credible interval will get narrower and narrower the higher n is. The reason is the higher n is, the lower the variance. You see, if n is going to be really, really high, then those will get small. So, okay, let's move on. I think that's enough examples of Bayesian inference for now. We'll do more exercise like that, and there are also some on the tutorial this week. So let's do hypothesis testing. We did a very quick introduction to hypothesis testing. You will already have done an introduction to hypothesis testing in your first year statistics course as well. But let's try and do it from the ground up. So, so we're back to the frequentist world. There is actually a Bayesian way to test hypotheses, which is kind of, but we're not going to do that. So it's just basically, if you're in the credible interval, then you accept. If you're not, then you reject. So we'll focus in the frequentist case. So the hypothesis testing, you have a null hypothesis. And I have to say, there is something that is really distressing in these notes, the chapter 10, which is on the website from previous years. The thing that, okay, so we have I'll say it in a moment. We have a null hypothesis and an alternative hypothesis. That's always H0. The alternative hypothesis, whether you like it H1 or HA, I don't mind, or capital A. So the null hypothesis and the alternative hypothesis, they are sort of in contradiction to one another, but it'll sometimes, especially in the one-sided case, it'll not necessarily be that they're mutually complementary. So I'll just say usually, but not always, HA says that, it's the same as saying that H0 is not true. Okay, so the not always relates mostly to the one-sided case. But usually we're just looking for evidence against the null hypothesis. Now, one thing that we're not looking for is evidence against the alternative hypothesis. And the reason is H0, okay, we're talking about parametric statistics, of course. There are non-parametric versions, but we're focusing on the parametric case, which is that the observations, whether they're IID or not, okay, usually they're IID, but even if they're not, some distribution depending on parameter or parameters. Okay, I'll say theta and underline just in case it's multiple parameters. So those are your observations. And then you don't know what the parameters are, but if H0 is frequently that theta has some particular value, not always, but frequently. But it tends to be a very restricted, like theta has all, in principle, could be anywhere on the real line, and then there's just one particular value that I think it is. So there's not, what I'm saying is there's not a symmetry between H0 and HA. Quite the opposite. It's very asymmetrical. There is H0, a null hypothesis is this is kind of a philosophical question. What we would be prepared, we don't know it's true, to accept as true in the absence of countervailing evidence. Okay? Now, because of the fact of these parameters being continuous, the fact that we're, short of evidence against it, we're happy to accept H0 as true, does not mean that we're happy to declare HA false in the absence of evidence. It's more subtle than that. And particularly the reason, if you think H0, for example, in the case of a proportion, you would say H0 P equals P0. Or, in the case of a mean, H0 mu equals mu 0. So this is some P0 and mu 0 will be known things, like I think the probabilities are half, or I think that the mean is 10. So those will be known. So just because I would be prepared to accept the probability is a half without evidence doesn't mean I would be, rigorously against it being something other than a half. The reason is it's very hard to tell P equals a half from P equals 0.51, or even harder to tell P equals a half away from P equals 0.505. So that's why H0 is something we're comfortable with, but that doesn't mean that we're until we see evidence against it. But that doesn't mean that HA is something that we're uncomfortable with. It just means H0 is what we're focusing on. And so just to specify the part of the notes that I must criticise, they're talking about type 1 errors, and we'll talk about this in a moment. So, if HA is rejected, now, okay, here's the thing. HA is never rejected. Okay. Instead, so what they're thinking about is something that is consistent with H0. If you find, so say you think the proportion is exactly 50%. Then you do a survey and you find out of 1,000 people you have 502. 502 out of 1,000 is pretty consistent with a half. So we would then be happy not to reject the null hypothesis. But that doesn't mean you're rejecting HA. Because if instead, what you say is we fail to reject H0. Okay. For example, you'd have something like H0 P equals a half, and then 502 out of 1,000 observed, successes, if we think successes, we do not reject H0. Now, I haven't done the calculation for that yet, but you can probably see that 502 out of 1,000 is well within the margin of error. So we would not, but we'll do the calculation in a moment. So we do not reject H0 in that case. That's not the same. That's not the same as rejecting HA. Because, the alternative hypothesis, and HA is that P is not equal to a half. That's the usual alternative. Even if you had a one-sided, it would be that HA is that P is strictly greater or strictly less. You'd never reject HA because HA is so close to H0, right? HA includes the case where P is just a tiny bit away from a half. So if you're happy to accept H0, you'd also be happy to accept a certain range of the HA. So we never reject HA. The only thing that can happen is we either do reject H0. So on the other hand, if instead of 502 I got 800, then we'll do the calculation, but that would seem outside the margin of error. So then we would reject H0. And if you reject H0, then it seems like HA is the only possibility left. So we would reject H0 in favour of HA if it was far away. But if it's close, all you say is we do not reject H0. So that's kind of a vague conclusion. We don't even say, some people say, okay, so that's the context of that notes. So if the probability of the observed value being as extreme as x or more. So this is kind of the way we think about the rejection. As extreme or x as more is less than the significance level alpha, which is usually 5% or less, but then we reject H0. Otherwise, we do not reject H0. And so historically, I guess it was kind of common to say accept H0. I'll just say that's not quite as good a way to say it. It's sort of the same as accepting H0. But to the extent that accept is a positive word, the positive part of accepting H0 comes from the fact that I was prepared to accept it at the start, right? If I think that my coin is fair, then I'm prepared to accept that at the start. If I then flip the coin 10 times and get 6 heads, it's not so much that the 6 out of 10 is telling me the coin is fair. It's more that I thought the coin was fair to start with, and I haven't found anything to disabuse me of that notion. So, okay, I better do it. Well, let me do it 4 times. It has to be some. Okay, tails. A bit boring if I don't. I think it's fair. Heads. Had to do this once. Tails. And heads. Okay, so 2 tails and 2 heads. Now, if I just got... Now, say I couldn't see that it's actually a coin and looks fair. Say it was just some computer button where I pressed it. If I just did it 4 times with this button that opaquely said either heads or tails, if I just got, head, tail, I wouldn't necessarily conclude that it's a fair coin from that. I just think that, oh, well, it's consistent with it being a fair hand. Because, of course, 4 samples is a very small number of samples. It's only if I got something way out of proportion, and even 4 is not enough to see it, but if I had 6 coin flips, say I had 6 coin flips, and they were either all heads or all tails, the chance of getting either all heads or all tails among 6 coin flips is 1 on 32, because it's 1 on 64 plus 1 on 64. So 1 over 32, that's less than our somewhat arbitrary but common threshold of 5%. So if in 6 coin flips I got the same thing all the time, that would provide me, I think, strong evidence that my method was not a fair coin. But just because I got 4 out of 6 coin flips heads and 2 tails, it wouldn't tell me specifically that we should accept it's a fair coin. That acceptance would only be from the fact that you're happy with the null hypothesis in the first place. So much is kind of the philosophy of hypothesis testing, and that's why. Now, this probability, as you probably know, has a special name. The probability of the observed value being as extreme as x. So, okay, by the way, x, often I put an underline just to say that it's all the observations together. It's like if I have multiple parameters, I put an underline to say I just mean all of them together. So if the observed value is as extreme as the one as more, and so extreme is a property that remains to be defined. We'll define that in a bit later. But just in generalities, this is called the p-value. Okay. So p-value is the probability of observing something as extreme as that or more. And so that makes sense because I think H0 is true a priori for other reasons. It's just a sensible, it seems to make sense. It might be like a scientific theory which we believe to be true, but we're looking to see if we can disprove it. And then if we do find evidence against it, such that the chance of getting such a bad result just by chance is less than alpha, then we reject it, and alpha is called the significance level. So if it's less than the significance level, p less than alpha, reject. Okay? And if p is bigger than alpha, we do not reject. I'm specifically being vague about p equals alpha because that pretty much never happens. So it doesn't matter. Different people would have different points of view. But certainly if it's less than alpha, we reject, and if it's greater than alpha, we do not reject. So old textbooks will sometimes say accept H0, but just so long as you know the acceptance is not a strong endorsement, it's just acceptance through apathy. So let's go on and do some examples. Now, with hypothesis testing, we can often do something slightly better than we can with confidence intervals, and that's because the hypothesis gives an extra piece of information to feed in. And let's tests for proportions are the critical examples of where you do slightly better. You have less approximateness when you do that. So test for proportions, and because I mentioned it, I'm going to mention that there is this exact test. So your x, if you like, your observations are x1 up to xn. Like I just flipped the coins, they're IID Bernoulli p. Okay, and the independence of them is an important assumption, but when you saw me flip the coins, it makes sense that they're independent because there's no physical linkage between one flip and the next flip. It's done so if something is done in a physically independent way, it's natural to assume there's nothing in common, unless you can think of a common factor that's random applying to both of them. So if they're IID Bernoulli, the summary statistic that is useful, of course, is P, which is, normally we called it K over N, but normally we just say we're talking about a binomial. Of course, x1 up to xn is a binomial NP, and then I divide that by n. So because I didn't introduce K, I have to write P equals x1 plus dot 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 plus xn over n, and I should have said, of course, that's P hat. That's not the actual P. That's P hat. So that's the observed. Now, P hat is actually sufficient statistic. You can, we're not going to do a lot about sufficient statistics, but once you know P hat, there's no further information in the x's that is helpful. So, so the exact test, this is actually called the exact binomial test. It's only practical when you can actually calculate the exact binomial values, which you can in R, but you won't be given binomial values on the exam. So if H0 is that P equals P0 versus H8, let's say the two-sided, this is two-sided, because two-sided means I'm looking for evidence that P is bigger or less. The test statistic, now this is not the same as the pivotal value that we talked about before, but it's often related. The test statistic is something you can calculate from the data and the null hypothesis. So in general, something you can calculate from the data. So this is the general meaning of what a test statistic is. That has a known distribution if H0 is true. Okay. We can't talk about the probability of H0 being true or not because we're not being Bayesian here, we're being frequentist. All we can say is that H0 is either true or not, we don't know which one it is. But if it's true, then the test statistic has a known distribution. And the exact binomial test, of course, is that k, which is np hat, which is equal to... so I'm doing the exact binomial test first, np hat, which is x1 plus dot 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 plus xn. The known distribution is binomial np0, okay? So in this case, the known distribution is binomial np0. And then the p-value, how do we make sense of the p-value? Well, it's as extreme as this or not, or worse. Because it's two-sided, we're looking for evidence that the true proportion is either bigger than that or smaller than that. That means as extreme or worse means both sides have to be taken into account. So I have to do the p-value, which... so the p-value is going to get totally confused with little p there. So I'm just going to say the p-value is the probability that the observed k minus its mean. Mean is our relevant centre, and that's np0, is greater than or equal to k, the observed value of k, minus its centre. So if less than alpha, we reject H0. Okay? So this is a funny kind of a thing. And so let's do an example, which was the case of a slightly... let's the one that I said in words. 6 coin flips, and all come up the same. Is the coin biased? That's the question. Okay. Is the coin biased? Well, you would do it by saying the p-value is... So H0 is that p equals a half versus H alternate that p is not equal to a half. The p-value is the probability that observed... So k is binomial 6 1/2. And I'm giving the null hypothesis distribution. That's what's relevant for the p-value. So under the null hypothesis, k minus 3 is greater than or equal to 6 minus 3. Whether it was heads or tails, if it was heads you would have got 6. If it was tails you would have got 0. But because we're looking for a two-sided test, we have to include both tails. So that's the probability. Because k is a binomial, it only takes the values 0 through 6. K equals 0 or 6, and that is equal to 1 over 32. Okay, and that's less than 0.05. Okay, so we reject H0, and if you're at the 5% significance level. And that's a way of saying there is significant evidence that the coin is biased. You know, you can't be certain. It's possible to get, even if the coin was fair, it's possible to get this happening. So you can't be certain. We would just say there is evidence that the coin is biased. Okay. So if you had got something less extreme, you would have got p bigger than 0.05. You wouldn't have said, we conclude the coin is fair. That's too strong. You would say something like, the evidence is consistent with the coin being fair. Consistent doesn't endorse it any more than saying it could happen. Okay. So if you got, you know, p greater than p value greater than alpha, something like, say, there is no evidence from this test, you know, there might be other evidence from this test that the coin is unfair. Okay? That's the most you can say. You can't say the coin is fair. It might or it might not be. But there's no evidence from this test that the coin is unfair. or no good evidence. Okay. So that's how you do it. Now, there are some other ways of thinking about, so the alternative approach is the rejection region. And this is more the one that was done more historically, mainly because people had tables. Because to calculate the p-value is very difficult often, or especially an exact binomial test. You have to add up. It was easy because there's only two values here, but in general for a binomial, if you're saying binomial is bigger than 30, you have to add up 30 plus 31 plus 32 plus. You have to add up all the different mass function values. So that's very boring. So the rejection region is a way of saying it's the set of all observation x that would give p value less than alpha. So they're the set of observations that would reject. And then you can calculate the rejection region ahead of time, particularly if you have quantiles. So that's often what we do. So if x is in the rejection region, you reject H0. So it's sort of the same as the p-value approach. You're just calculating the region ahead of time. And you can do that with quantiles. If not, because frequently, if you have the 5% quantile, you can find the rejection region. You can't find the exact p-value. It's something complicated. If not, do not reject H0. Okay, so let's talk about the approximate. So the exact is not very important because you can't do it without a binomial table or without something to calculate the binomial probabilities. The approximate binomial test. The approximate binomial test relies on the approximation binomial NP0, approximately normal NP0, NP0, 1 minus P0. We know that. And you do want to test your hypotheses NP0 at least 10, 1 minus P0 at least 10. That's for a good. That's a rule of thumb, but it's a rule of thumb for a good approximation. Now you can do that because you have a H0P equals P0. Now let's this time do a one-sided test, just because we haven't done a one-sided test so far. So we're looking for evidence that the probability is greater than what I think, and I couldn't care less if it's less. I don't want to reject H0 if it's less. So one-sided. Now, usually a one-sided test is phrased in this fashion. Sometimes, to be maybe pedantic, people would say the H0 is also a region, P less than or equal to P0. But that doesn't change anything. You still treat it as P equals P0 for the purpose of calculating. Because if it's further, you would just have a less stringent test. So sometimes people write H0 P less than or equal to P0, but what they really mean is it's the same as P equals P0. And then the test statistic. So first check this rule of thumb. If that rule of thumb is not true, then the approximate binomial test is too approximate, even at the 95 confidence level. Now, this rule of thumb is actually not good enough if you wanted 99.999% confidence. Then you would need a better. But this is good enough at 95%. So the test statistic is, it's always a Z because it's you just standardize. So the observed p hat minus p naught divided by square root p naught, 1 minus p naught over n. Now, depending on whether you have that or the other one, you'll get the exactly same thing, k minus np0 divided by square root np0, 1 minus np0. No, np0, 1 minus p0. Okay, so reject if Z is greater than Z alpha, which is about 1.68 if alpha is 0.05. You can look that up in the normal tables. So this is the one that has 5% of its mass on the right. Okay, so that's your approximate binomial test. So you do have to check that thing first. This is still better than what you're doing for the confidence interval because you have the actual P0 value. So it's still more precise than the corresponding confidence interval. That's why, just to pick on these notes one more time, at the back of the notes, it says there are 3 equivalent ways to do a hypothesis test. Standard or rejection region or attained significance level. you calculate the actual p-value. Now, historically people did this because you couldn't calculate the actual p-value. And on the exam, that's probably a good approach too, because still without R or a computer package, you can't calculate the exact p-value. So that's a good one. Now, the confidence estimation says that you reject the null hypothesis if theta naught lies outside the confidence interval. It seems